Okay, so this lecture is on linear dimension reduction, and one of the most common methods of linear dimension reduction is principal component analysis. Today we shall look at what's principal component analysis. So our goal here is to reduce the number of dimensions. Typically, we are provided with a lot of sample points which are in very high dimensions, although in this figure here, what's shown is two-dimensional data, and that's in the scatter plot here. And the goal is to reduce the number of dimensions. The number of dimensions in our figure here can only be when you reduce the number of dimensions, it can only be one dimension. And in order to reduce the number of dimensions, what we have to do is, in PCA, we exploit the covariance of the scatter plot. So you can see that it's not like they're all randomly scattered. There is some covariance between the two-dimensional points, and that's what we have to exploit in PCA. So what we have to discover in PCA is a direction of maximum variance. So you see this red dotted line here, and if you project these points along that red dotted line, the variance turns out to be highest. And so that direction is the first principal component. So this direction is V. That's the direction of maximum variance. And since it's a direction, the L2 norm of V is 1. In other words, it's a unit vector. And we have to find out what this direction is. We have to, in other words, compute this unit vector. And that's the first principal component. So let's see how we do the dimension reduction. So here in this scatter plot, we have two-dimensional data, and then we have discovered, using principal component analysis, which we shall see later how to do that, we find a direction V, a unit vector, and that gives us the maximum variance. How do we project the sample points, all these x's, along V? What we have to do is simply take V transpose x, and this length here from the origin to this red point here, V transpose x, so that is the projection. And then in a similar manner, we can project another point to this red dotted line, which is defined in terms of this unit vector V. And then we proceed with a third point, and likewise we continue with all the points, and so what we land up with is all these projections along this red dotted line. And so these projections are the reduced dimension, which is in our figure, it's simply one dimension. And so the V that we found out is called the first principal component. And then our next goal is to find out another direction that is orthogonal to the first principal component. The first principal component is the red line, and so the green line is the next direction. It has to be orthogonal to the first principal component, and yet it has to maximize the variance with that constraint. In two dimensions, it doesn't make that much sense because you only have one dimension left once you have extracted the first principal component, or the first PC. But if you had more than two dimensions, if you had three dimensions, that it makes more sense. So you can find out the direction of maximum variance, that's V1. Then you can find out another direction, V2 of maximum variance, that's orthogonal to V1. And then that's the second principal component. And then the third principal component will be yet another direction, V3, that maximizes the variance, but under the condition that it's orthogonal to both the first and the second principal components. It looks even better if we center the data around the origin so that the average, the mean of the data is the origin. And so you can see the three directions, V1, V2, and V3 if it's three-dimensional data. So let's see how to begin. We begin by centering the data. So the data points that are provided are in this form. They're vectors in d dimensions, and we have n of these samples here. This is our data, and so they are xn, where n goes from 1 through uppercase N. And the data matrix, we can organize these sample points into one big matrix, and each sample point is actually transposed and it forms a row of this data matrix, which is uppercase X. And since we have n samples, this uppercase X, this matrix here is a n by d matrix. And the mean is 1 over n of summation of xn. That's the mean. And so let's see how to center the data. If once we have the mean, which is x hat of all the data points, so the centering is simply subtracting x hat from each sample point. And that's when you do it sample by sample. Now, when you have to do it in a single operation in terms of the data matrix uppercase X, this is in fact what you do. X is replaced with X minus 1 over n, where n is the number of samples, and times 1 transpose X. This bold 1 is a column vector of all ones, and this 1 transpose is a row vector of all ones, and X is of course our data matrix. And to see why this is equivalent to translating each of these points xn by an amount x cap is like this. So X is the data matrix, and each row of this data matrix is a sample point transposed, and then minus 1 over n, 1 transpose. It's best understood if we retain this 1 here and we express this 1 transpose in terms of the scalar ones here. It's a row vector of all ones. This 1 transpose, we replace it with, we explicitly express it in as a row vector of all ones, and so this x is this x here. And then when you do this multiplication, you see that this 1 and this 1, 1, 1, 1, all of these are replaced with bold ones. These are row vectors. And when you do this multiplication, eventually it turns out to be this. X1 transpose until xn transpose. So these are, each row is the sample point. And what you are in fact subtracting from each row is 1 over n times x transpose 1 plus x transpose 2 until x transpose n. And so this is the summation of all the samples. 1 over n of that gives you x hat, which is the mean, and that's being subtracted from each x transpose here. So before the centering, this is what the scatter plot looked like. And after we centered the data, this is what it looks like. So the covariance matrix, uppercase lambda, is given by 1 over n summation of xn minus x hat xn minus x hat transpose, and this covariance matrix is a d by d symmetric matrix. Why is it symmetric is going to be evident in just 2 more steps. So simplifying this expression further, we get 1 over n summation xn minus xn transpose, minus x hat transpose, and this second term here is outside this summation sign, This simplifies to 1 over n x transpose x. This is the data matrix uppercase X, and minus x hat transpose. And you can see from this expression here why this lambda is symmetric. All you have to do is take the transpose of this. You can get back the same expression, which shows that the transpose of lambda is equal to lambda itself. So now let's move on to devise the first principal component. So the direction of the projection, we are looking for a direction which is this W, a unit vector W, and the projection of each sample point xn along this projection is W transpose xn. Note that W is not known yet. We have to devise a proper direction W. The projection of the mean of the samples x hat is likewise W transpose x hat, and the variance of the projected points is given by this expression here, and each of these here, W transpose xn, W transpose x hat, these are all scalars now. So the covariance matrix is replaced by simply the variance. I still use the transpose here so that this whole expression can be simplified further. So taking the transpose inside, what we have is W transpose xn is replaced with x transpose and W, and W transpose x hat is replaced with x hat transpose W, which is equal to, now I take this W transpose outside because it's independent of the index n, and that's here, and I take this W outside, and that's here, this W here. What's inside this parenthesis is 1 over n summation of xn minus x hat, xn minus x hat transpose, and this is simply the expression for the covariance matrix lambda. Therefore, what we have is W transpose lambda W. In other words, the direction of the projection is W, and the variance of the projected points is W transpose lambda W. And what we need to do is, our goal for principal component analysis is to maximize the variance. So we have to choose a W that maximizes this variance, W transpose lambda W. So what we have to do now is to maximize the variance, which is equal to W transpose lambda W here, and we can now formulate PCA, the principal component analysis is PCA, as a constraint optimization problem. So what we have to do is maximize with respect to W transpose lambda W. This is the variance of the projected points, and W is the direction of the projection, and the constraint is subject to W transpose W equals 1. What does this mean? This constraint simply means that W is a unit vector. Let's construct the Lagrangian of this constraint optimization problem. So we have LW mu equals, the objective function is W transpose lambda W, which is this term in the Lagrangian, and I choose this negative just for convenience. And then we have a mu Lagrange multiplier times W transpose W minus 1. That's the Lagrangian. And differentiating this Lagrangian and equating to 0, what do we get? So the first term differentiated is twice lambda W. Remember that lambda is the covariance matrix, which is a symmetric matrix, minus twice mu of W. That's this term, and that's equal to 0. This implies that lambda w minus mu w equals 0, or in fact lambda w equals mu w. And this is the definition of an eigenpair. So lambda is the matrix and w is an eigenvector and mu is the corresponding eigenvalue. So now we know that the principal component is, the first principal component rather, is a eigenvector of the covariance matrix lambda. The question is which which lambda to use to maximize this? And the answer lies in spectral decomposition theorem. So what should be W? We know that W will be an eigenvector of the covariance matrix lambda, and from the spectral decomposition theorem we know that it's going to be the eigenvector with the largest eigenvalue. So it's going to be V1. So this is what we have. This is our constraint optimization problem, and the solution is W equals V1 here, the first eigenvector. And what's the variance along the projection V1? It's V1 transpose lambda V1, which is equal to mu1, which again comes from the spectral decomposition theorem. So this is the data, the scatter plot of the data, and V1 is shown, that's the first principal component. Now let's devise how to obtain the second principal component. The problem statement is the same as before. We have to maximize the variance of the projected points, this time along the second principal component. So the constraint optimization problem is the same as before. Mostly we have to maximize with respect to W the variance of the projected points, which is W transpose lambda W, subject to the constraint that W transpose W equals 1, so that W has to be a unit vector. But we have another constraint, that is W transpose V1 equals 0. What it means is that this new principal component has to be orthogonal to the first principal component. The second principal component is orthogonal to the first principal component. And what's the solution? The solution, again from spectral decomposition theorem, the solution is W equals V2, the second eigenvector of the lambda matrix, the covariance matrix. And what's the variance along this projection? That's V2 transpose lambda V2, which is the corresponding eigenvector lambda 2. I normally use lambda to refer to eigenvectors, but remember that mu is also a Lagrange multiplier corresponding to an equality constraint, which is why I had to compromise my notation a little bit. So this mu is an eigenvalue. So this is V2, the second eigenvector, and it's orthogonal to V1, the first eigenvector, because lambda is a symmetric matrix, and symmetric matrices have orthogonal eigenvectors. So V1 is the first principal component and V2 is the second principal component. Likewise, V3 is the third largest eigenvector of lambda, and that's the third principal component. So a pattern emerges. The first principal component is nothing but the first eigenvector V1 of the covariance matrix lambda. The second eigenvector is V2. The second principal component, is V2, the second eigenvector of lambda, and so on. The dth principal component is the dth eigenvector of lambda, and so on. Now, instead of extracting the first principal component, then reformulating the problem to extract the second principal component, and keep on doing so step by step. Let's try to devise one formulation for all the principal components. And so what we have is we require m orthogonal directions, uppercase M, and this m is obviously less than d, the dimensions of the data points. And so these are the directions W1, W2 until Wm. And we can concatenate these vectors W1 through Wm into one matrix, uppercase W, and that gives rise to this maximization problem. So what we have to do here is we have to maximize W1 transpose lambda W1 plus W2 transpose lambda W2 all the way until Wm transpose lambda Wm. What do these terms mean? This first term, W1 transpose lambda W1, is simply the variance of the projected points along the direction W1. W2 transpose lambda W2 is the variance of the projected points along W2, and so on. And the constraint is subject to W transpose W equals I, the identity matrix. Why this constraint? This constraint simply ensures that all the W's are mutually orthogonal to one another, and they're also unit vectors. So now let's look at this W transpose, uppercase W, that's the matrix, times covariance matrix lambda W. And this W is given by this equation here. W is a matrix whose individual columns are the directions that we want to obtain. And so W transpose is this matrix whose rows are the transpose of those directions times lambda times W. And when we do the multiplication, we get this large matrix here. And so look at this term, W1 transpose lambda W1 is this term here. Take W1 transpose lambda W2, that's this term here, and so on, until the last term would be Wm transpose lambda Wm, which is this term here. And now the trace of this W transpose lambda W is given by this. The trace of a matrix is the sum of the diagonal elements. So these are the diagonal elements, and we add them up together, we get this summation here, which actually is the same as this objective function that we want to maximize. In other words, what we want to maximize is the trace of W transpose lambda W, where W is a matrix whose columns are the directions that we want to obtain. So these observations lead to a reformulation of PCA as a problem of trace maximization. So we want to find a matrix uppercase W whose columns are lowercase w's, the directions that we are looking for, in such a manner that the trace of W transpose lambda W is to be maximized, and the constraint is W transpose W is equal to the identity matrix. This ensures that all the lowercase w's are mutually orthogonal and unit vectors. And the solution is W equals V1, V2 until Vm. These are the rows, the columns of the matrix uppercase W, which are the eigenvectors of the covariance matrix. And how did we get this solution? The answer lies in the Courant-Fisher theorem. So these are the steps in PCA dimension reduction. What's given is the data matrix, which is an n by d matrix, and d is the number of dimensions, which is typically high, and n is the number of samples. And the covariance matrix computation is the first step of PCA. So lambda is given by this expression here, and that's a d by d matrix. The next step is to obtain the spectrum of lambda, the eigenvectors v1 until vm. These will give rise to this matrix W, which is a d by m matrix, where m is the number of dimensions that we want to keep. And so the reduced dimension data Y is simply X post multiplied with W, and that's an n by m matrix. So we had originally X, which was a n by d matrix, where d is the higher dimensions, and then after PCA what we are left with is an n by m matrix, and m is the number of desired dimensions. With this, we conclude our lecture on principal component.